Hello everybody. Today we are going to discuss a very important topic known as application of propositional logic, section 1.2. Introduction. Logic has many applications to mathematics, computer science, and numerous other disciplines. Statements in mathematics and the science, as well as in natural language, are imprecise or ambiguous. To make a statement precise, they need to be translated into the language of logic. Propositional logic and its rule can be used to design computer circuits, to construct computer programs, to verify the correctness of program, and to build expert system. Translating English sentences. One reason for translating English sentences into expression involving propositional variables and logical connectives is to remove ambiguity. Once we have translated the sentences from English into logical expression, they are easier to analyze for their truth values. Example 1. How can this English sentence be translated into a logical expression? The problem statement: you can access the internet from campus only if you are a computer science major or you are not a freshman. Solution: first thing is we assign different statement to different variables. So for instance, let us say let B be you can access the internet. Also let C be you are a computer science major. Let F be you are a freshman. So to write this from the above there, you can see that in order to write this into a mathematical expression, we say if A, then C or negative F. This is the expression that we can get from this if we translate this expression into a mathematical expression. AND gate. AND gate is this gate that have a D shape. It has two inputs, so it produces the value 1 if and only if all the operands are 1s, and otherwise it has a value of 0. So the mathematical expression of this is shown below here. Also, we have a truth table for the AND gate, and you can see here when we AND 0 and 0 we produce a 0. When we AND 0 and 1 we get a 0. When we AND 1 and 0 we get a 0. But when we AND 1 and 1 we produce a 1. Also, let's talk about the second logic gate, which is known as OR gate. The OR gate produces the inclusive OR function, that is, the output is 1 if input A or input B or both are 1s, and it's 0 otherwise. So the mathematical expression of the OR gate, or the mathematical translation of the OR gate, which has two inputs, is shown below. Also, looking at the truth table, you see that when we OR 0 and 0 we produce a 0. We OR 0 and 1 we get a 1. 1 OR 0 is 1. 1 OR 1 is 1. Let's talk about properties of AND and OR gates. We have one property which apply to both of them. This property is known as commutation. So commutation of when it applies to AND gate or to AND operation, we may say A and B equals to B and A. That means here in commutation operation, we can see that A and B exchange places. They exchange places. When we apply commutation to OR gate or to OR operation, we say A or B equals to B or A. So you can see here that B and A exchange places. So when we exchange places in the operation of OR or operation of AND, we get the same result. Properties of AND and OR. Another property that applies to both AND and OR is the so-called the associative property. For instance, A or parentheses B or C equals to parentheses A or B parentheses or C. So the same thing to AND. A and parentheses B and C equals to parentheses A and B and C. Properties of AND and OR. So the third property is known as distributive property. Distributive property is the same as the distributive property that you know of in algebra. The only difference here is that we apply it for logical expression, or we apply it for binary system. So if you have an expression A and open parentheses B or C close parentheses, we can distribute this A outside into the parentheses, and then the expression would become A and open parentheses B or C close parentheses equals to A and B or A and C. We have the inversion, which is also known as NOT. So an inverter has one input and one output. So when we run the input A through the inverter, what we get is an output negative A. So take a look at the truth table of the inverter. Exclusive OR, XOR. So exclusive OR symbol look like the OR gate, except that there is an XOR line in front of the OR gate. So either A or B, but not both. So when A or B are equal, the output is usually 0, but when both of them are not equal, the output is usually 1. Sometimes this gate is known as the inequality detector, because the result will be 0 when the input are the same and 1 when they are different. Getting the XOR to to be 1. There are two ways of getting S, or the output of the XOR, to be 1, as is stipulated here in this truth table. More complicated digital circuits can be constructed by combining these basic circuits. We mean by basic circuits the logic gates. So everybody knows about microprocessor. So microprocessor is basically constructed using the main component in there is the logic gates. So logic gates are very important in our daily life. So example 2, we are required to build a digital circuit that produces the output P or negative R and negative Q or negative P or negative R. So the solution of this problem is found in your textbook, page 21. These are the references that we use to create this PowerPoint.